with a third order forward amp. Okay. And so what do we so now the loop gain function is nothing but A1 cube times f divided by 1 plus s over omega 1 the whole cube, because identical stages are assumed. So, the closed loop gain V O by V I is nothing but 1 over f times 1 over 1 plus okay. So, now the question is, where are the poles of the closed loop system? So, poles are roots of one plus s by omega 1 the whole cube by A1 cube f equal to 0. Correct, which basically means that this is minus 1 and this goes up there. So, that is basically A1 cube f. Correct. So, if 1 plus s over omega 1 the whole cube is minus A1 cube f, what is 1 plus s by omega 1? A1 f to the 1/3 times, I mean how many roots must be there? 3 roots. Okay. So, what are the roots? One is okay, let me, so let us say x cube is equal to 1. What are the roots? What are the roots of this equation? Huh? What is omega? Okay, e to the j. Okay. So, now tell me what is 1 plus s by omega 1 here? Minus 1. Okay. What is this? J root 3 by 2, 1 minus j root 3 by 2. Okay. All right. So, So, that is 1 plus s over omega 1. So, what is s itself, or what is s over omega 1 is minus 1 plus a 1 f whole sorry a 1 f to the 1/3, correct, times minus 1 plus minus j root 3 by. Okay. So, s basically is this times omega 1. Okay. So, when so if we plot the locus of the root, so we now need to figure out whether this is, I mean, where these poles are. Where do we want these poles to be? For stability, we hope that they will be in the left half S plane. So, let us see where they are. Of course, they depend on, clearly the location of the poles depends on a 1 f to the 1/3, right, which is the cube root of the DC loop gain, right. Okay. So, when a 1 f to the 1/3 is 0, where are the when it is tending to 0, what comment can we make about the poles? How many poles are there? 3 poles. So, where are the 3 poles? Minus where are the poles? Yeah, we got the equation. Now, can't we figure out where the poles are? Huh? I mean, this whole thing is multiplied by omega 1. So, as a 1 f tends to a 1 tends to 0, where are the 3 poles? Why? Yeah. So, basically, minus a 1 f, this I mean this is the 3 vectors there. The magnitude of all the 3 vectors is so sorry, they are pointing in 3 different directions, but the magnitude of the 3 vectors is the same and is very small. So, you have basically as a 1 f as a 1 tends to 0, you have 3 poles at minus omega 1. As a 1 f keeps increasing in magnitude, or a 1 f to the 1/3 keeps increasing in magnitude, what happens to the poles? So, this as a 1 f becomes more and more, then what comment can you make about minus a 1 f to the 1/3? So, one path, this is standard root locus plots, so one path will go in this direction, correct. What about the other 2? They will be, what is the angle? What? Okay, so this is so for sufficiently large a 1 f to the 1/3, what comment can we make about the location of the poles? What will move to the right side? How many poles? For very large A1 F to the 1/3, what will happen to the location of the poles, man? Maybe you're getting confused because you're a left-hander. Huh? Which is left and which is right? So as A1F keeps becoming larger, this is going this way, these two are going this way, one is going this way. So can you please tell me what is happening to the poles? There's nothing, no calculation to be done, man. Just take a look at that picture and tell me where those poles are going, Baba. Yeah, so as A1F keeps becoming larger and larger, at some point there will be two poles definitely in the right half S plane, right. So basically, one immediate conclusion is that for a sufficiently large A1F to the 1/3, two poles will be in the right half. Okay. They are clear? So now this is bad news because the system in the closed loop system, I mean the first and second order systems were at least the first order system was nice and stable, except that we couldn't get the large loop gain that we wanted at DC. The second order forward amplifier was technically stable, but in practice if you wanted a large loop gain, then you would get a lot of ringing, right. The third order system is basically outright, for a sufficiently large this thing, it's very clear that two of the poles will lie in the right half S plane, correct. Now the question is, well, if the poles go into the right half S plane only when A1 F to the 1/3 is 10 million, then we do not have to care, right, because that DC loop gain is very large anyway. So what we need to do is, we need to figure out how large a DC loop gain we can use, so that the poles are still lying in the left half S plane, right. That is a logical question to ask, correct. In other words, how large can I make A1F to the 1/3 while the poles still are in the left half plane, right. So the critical point is, to answer that question, we say, okay, well, for what A1F to the 1/3 will the poles lie on the j omega axis, correct. So how will we figure that out? So what are those two poles? Those two poles are -1 plus A1F to the 1/3 by 2 plus minus A1F to the 1/3 by 2 times root 3j, correct. So this is the real part of the root, and therefore if the two poles lie on the j omega axis, correct, what happens? What should the yeah, so this is 0 for A1F to the 1/3 equal to 2, correct. So therefore if A1F to the 1/3 is 2, this means that the DC loop gain is what? A1 cube times F, which is equal to 8. alright. So, what is this telling us? If you have a third order system with identical poles, then even with a DC loop gain of 8, the closed loop system's poles, 2 of the closed loop system's poles are on the j omega axis. Okay. And for A1 cube f greater than 8, the closed loop system, 2 of the poles of the closed loop system are actually in the right half S plane. Correct. So, that is basically a terrible thing, right, because this now defeats the entire purpose of of using 3 stages. The whole reason to get to 3 stages was, we were getting what is attractive is that you can get with 3 stages of gain. If each stage has 100, the gain of 3 stages is 10 power 6, and therefore, that is a very nice thing. But unfortunately, even with a gain of 8, right, the closed loop system is unstable, right. So, we have a strange situation, when the gain, I mean, for the first order system, it's the system is stable unconditionally, but the gain you can get is very small. A third order system, you can get a large gain, but the system is unstable, correct. So, I mean, it's like you're in a company and you're hiring a person for your team, right. So, the first guy is basically is not very smart, but he can work very nicely with the team, right. Everybody likes him or her, right. But what can you say? I mean, unfortunately, person is not good technically. And now the other extreme is you have this person who is like super smart, right, but the person fights with everybody in the team, right, on the group. Okay. I mean, so that leads to a team which is unstable, correct, because you never know who is fighting with whom, and this way the project is definitely not going to get done, correct. So, you basically what do you want from somebody you want to employ? Oh, I am so happy you said that, and you didn't say the other one, So, a person is not technically good and he or she fights with everybody, then they'll be fired, okay. But basically what you're looking for is a good marriage between both these extremes, so that you get the high gain of the of the multi-stage amplifier and the stability corresponding to, I mean, basically the stability properties of a single stage design must somehow be married with the high gain possible with a multi-stage, correct. Okay. If this was done, then you have the best of both worlds, namely stability as well as high DC gain, DC loop gain. And to see what we can do,